All right, let's talk about climate change. We're always looking up at the sky or across the land for solutions, right? Solar panels, wind turbines, planting trees. But what if the biggest answer, the most powerful tool we have, has been staring us in the face this whole time? Today, we're diving into a really ambitious plan to engineer our oceans and turn the largest ecosystem on Earth into a powerful ally in this fight. When you think about it, it's kind of wild. We focus so much on the land we live on, but that's less than a third of our planet's surface. The other 71%, it's this massive solar-powered engine, constantly churning, constantly working. So the big question is, can we partner with this engine? Can we work with the oceans to help heal our planet?
Okay, so the first big idea for getting the ocean to help us out was something called fertilization. And on the surface, it sounded almost elegant in its simplicity. But it turns out it was a real double-edged sword.
So the logic was pretty straightforward. A lot of the open ocean is basically a desert, totally starved of key nutrients like iron. The idea? Let's go out there and fertilize it. The hope was this would cause these huge blooms of phytoplankton, tiny algae, which would suck up CO2 through photosynthesis. Then, when they died, they'd sink, taking all that carbon with them to the bottom of the sea. Simple, right? And yeah, on paper, it looked pretty tempting. A cheap way to pull down a ton of CO2, but the risks? Whoa. We're talking about potentially triggering toxic algae blooms, creating these massive oxygen-starved dead zones that kill everything, and just completely wrecking the marine food web from the bottom up. And the worst part? We weren't even sure the carbon would stay locked away. It was just way, way too big of a gamble.
So, okay, messing around with microscopic life, probably not the best idea. It's just too unpredictable. So researchers had to pivot. They started asking, what if instead of these temporary, chaotic blooms, we could build something bigger, something more permanent and stable? What if we could actually grow entire forests, but underwater?
And that was the real aha moment. This was the big shift in thinking. Forget these short-lived, unpredictable plankton blooms. The new focus became cultivating these huge, stable forests of macroalgae, like kelp. I mean, these things are just carbon-sucking powerhouses. Plus, they create these rich, stable habitats, the exact opposite of the chaos you'd get from a plankton bloom. Someone came up with this quote that just perfectly sums up how massive this challenge is, like building floating skyscrapers for seaweed in a stormy desert. Just think about that for a second. The open ocean is one of the most brutal environments on the planet. Building anything out there that could support a thriving forest, well, that's a monumental engineering challenge. So you can have a great idea, but that's not enough, right? It had to be engineered to solve 4 huge problems all at once. First, the structure itself had to survive monster storms and currents. Second, the kelps had to get sunlight near the surface, but it also needed nutrients, which are usually way down deep. And maybe most important of all, once you capture that carbon, you have to make sure it stays captured permanently. And the answer to all 4 of those problems, well, it came in the form of this single, really elegant design. This is where you see this beautiful marriage of biology and some seriously clever engineering. Okay, so here's the breakthrough. Imagine a kind of mesh, right? A scaffold for this underwater forest. But here's the trick. The mesh itself is also its food source. It's built with nutrients literally baked into the material. And these nutrients slowly release over decades, feeding the kelp right where it's growing. But the real stroke of genius is the second part. The whole thing is designed to sink after its job is done. So the whole life cycle for one of these modules is basically designed to be completely automatic. Step 1, you deploy this nutrient-rich mesh that's held up by biodegradable floats. Step 2, this huge seaweed forest grows on it for decades, just absorbing CO2 year after year. Step 3, those floats are engineered to slowly degrade over a set period of time. And finally, step 4, the entire structure, the mesh, all that biomass, sinks to the deep ocean, locking away that carbon for centuries. It's basically a self-contained, automated carbon sinking machine. Pretty cool, huh? Now, to really get how cool this nature-based design is, it's super helpful to compare it to the more, conventional, industrial way of capturing carbon. And the difference in strategy is just staggering. I mean, look at this. The biggest difference right off the bat is the energy source. Conventional carbon capture and storage, what they call CCS, it's a brute force industrial process. It needs massive, and I mean massive amounts of electricity to grab CO2, compress it into a liquid, and then pump it deep underground. The ocean forest, on the other hand, it runs on the most powerful and totally free energy source we have, the sun. It works with nature, creating new marine habitats instead of creating industrial risks like leaks. And that's really the fundamental flaw with conventional CCS. It's insane energy cost. The physics of trying to pull these tiny dilute CO2 molecules out of the air or out of a smokestack, it's just incredibly energy intensive. It is not a free lunch, not even close. And that energy cost leads to this number, which is just staggering, 5.4%. To capture just 1 gigaton of CO2 with conventional CCS, and that's just a fraction of what we emit every year, would use up 5.4% of the entire world's annual electricity production. Think about that. A single climate tool needing more than 5% of all the power humanity generates. And this is what makes that whole approach so incredibly problematic. If the huge amount of energy you need for CCS comes from burning fossil fuels, well, you end up emitting a ton of CO2 just to capture some CO2. It becomes this self-defeating cycle that completely undermines the whole point of the technology in the first place. Okay, so if we start to shift away from these super energy-hungry industrial solutions on land, what does a future that's built around the power of the ocean actually look like? What's the big picture here? The vision is really about a fully integrated, sustainable system out at sea. You'd have these huge zones of floating carbon factories, just soaking up CO2. They'd be powered by nearby offshore wind and wave farms. And at the same time, you'd have other operations focused on cleaning up all the plastic and oil pollution, while we expand marine sanctuaries to protect the natural biodiversity that makes the whole system work. And the potential scale here is just immense. If we really optimize this, ocean-based systems like these could be sequestering somewhere between 5 and 7 gigatons of CO2 every single year. To put that in perspective, that could offset a huge chunk of our global emissions. We're talking roughly 15 to 20%. Look, it's not a single silver bullet that solves everything, but it is a massive nature-powered contribution to the fight. And that really brings us to the final big question. The blueprint is there. We understand the engineering challenges, and the potential impact is crystal clear. So the question isn't really if we can do this anymore, it's if we will. The plan for a sustainable, productive blue future is sitting right there on the table. The next step is deciding if we're going to build it.